This lecture talks about the matrix representation of a linear transformation. First of all, remember in the previous lecture, it was shown that each linear transformations can be represented using a matrix, right? And if you have a linear transformations LA from Rn to Rm, then you have an n by n matrix A such that Lx equals to A times x, where x is a vector in Rn. Okay, so you can use a matrix instead of using definitions of linear transformations. And in these sections, we'll learn how to find matrix representation for linear transformations if you have a map going from Rn to Rm. Okay. All right. So definitions or theorem, if L is a linear transformation from Rn to Rm, which means L is a linear transformation from Rn to Rm, then this exists in matrix size m by n. M by n, okay? Such that if you apply the map onto a vector in Rn, right, then you get a result vector, and that result vector will be the same as when you're using this matrix A and multiply to the same vector. Okay. In fact, the jth column vector of A is given by, this is the j column of the vector A, and this is L, which is the linear transformations, and EJ, which is the unit vector. Okay, so this unit vectors here will be determined, and you know that if we look at our, let's say if we're in R3, okay, then the unit vectors, there are 3 unit vectors. So E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. Okay. And so on and so forth. So E1 is, so EJ here is the corresponding unit vector in the same vector space Rn. All right. Here's a proof. So if you determine, so let's say we in Rn, because the linear maps go from Rn to Rm, right? And for I goes to 1 to n, we define AI, which is the column vector of matrix A, equals to L times L of EI. And EI is a unit vector, corresponding unit vector. And then we let matrix A is a matrix whose column vectors are A1, A2 to AN using this definition. Okay. And then we always know that if you have a vector X, and again, we know that vector X here in Rn, and E1, E2, and En are unit vectors of Rn, then X is a linear combination of E1, E2 to En, because all the unit vectors will form a basis for a vector space Rn. Well, X is a linear combination of E1, E2, and E3, and you will have X1, X2, and Xn are the weights of these linear combinations. Then when you apply the map L onto the vector X, it's gonna be equals to, at first it will be, you know, L x1 E1 plus x2 E2 plus so on and so forth plus xn En. Okay. But then because L is a linear transformation, then you can move the constant out and split this whole vector into n different vectors here. And then by the definitions, LE1 equals to A1, right? LE2 equals to A2, and LEN equals to AN. So then Lx here will eventually equals to A times X, because A1, A2, and AN are the column vectors of matrix A. And X here is a vector X, the original vector is X. And because we're using unit vectors as a basis for Rn, then the vector X here, X1 and X2 and Xn are the entries of vector X. So we just show that Lx equals to A times X. And this definitions will help us find the matrix representation of a linear transformation. Let's do a couple of examples on how to find a matrix A, right? A representation matrix such as Lx equals to A times X. Okay. So we have first problem is we have a linear transformations from R3 to R2. Okay. So then we'll know that the matrix A that we're looking for has a size of 2 by 3. 2 rows, 3 columns. How can we find A? And we know that A1 equal to L E1, right? A2 equals to L E2, and A3 equals to L E3. Because we have 3 columns, so we'll make sure that we're going to have 3 columns of a matrix A. Well, what is L E1? So E1 is 1, 0, 0. By the definitions, the first in the results vector, the first entry will be the sum of the first 2 entries here. So 1 plus 0 is 1. And the second entries is always 0. So we know that LE1 is 1, 0. What about LE2? LE2 is L0, 1, 0 equals to 0 plus 1 is 1, and this is also 0. Okay. What about LE3? L0, 0, 1. 0 plus 0 should be 0. 0 plus 1. No, the second entries is always 0, so I don't have to do anything with it. I know that it has to be 0. So I found the 3 column vectors of A. Now my matrix representations A equals to 0, 1, 0, 1, and 0, 0 is the answer. All right. So the next problem is a linear transformation from R3 to R3, so it's just a linear operator, right? And since R3, so that means matrix A will have the size of 3 by 3. So it has 3 rows and 3 columns. Again, we know that A1 is LE1, A2 is LE2, A3 is LE3. So LE1 would be L 0, 0, 0 equals to, you reserve the first entry. The second entry will be the sum of the first and the second. So 1 plus 0 is 1, And the third one will be the sum of the 3 entries, which is 1. LE2 will be 0, 1, 0. And you would have this first entry is the same, and the second is here, and the third one is here. And LE3 should be 0, 0, 1. So it should be the first entry is the same, the second entry is the sum of the 2, so it's 0, and it is 1. Okay. Now we know that the matrix representations A equals to 1, 1, 1, 0, 1, 1, and 0, 0, 1. This is the matrix representations for this particular linear transformations. Again, you can always find a matrix representation for any linear transformation mapping from Rn to Rm.